Hello, hello, Professor Fiore here. Today's topic, simple digital gain control. What we're talking about is the control of an op-amp's gain utilizing a simple digital word. In other words, a parallel access. So with parallel access, this is easily performed with, let's say, a microcontroller. You could take one of the ports on your microcontroller, take, let's say, 4 bits, 3 bits, 5 bits, whatever, hook them up into this little circuit we're going to talk about, and by setting that digital word on the output, you set the gain of the amplifier, right? That's pretty cool. Now, 2 basic modes of operation. You can run from 0 to some maximum value. So if you had 4 bits, right, 2 to the n would be 16. So it's going to be 16 minus 1. In other words, a maximum gain of 15. So you go 0, 1, 2, 3, 4, 5, right up to 15. Those would be your gains. But of course, you could just multiply that out if you wanted to. In other words, you could go 2, 4, 6, 8, kind of like that. But that's the basic idea. All right, you just have this 0 to some maximum value. Constant increment. The second mode is that you can control the gain over a narrower subrange. So you could say, well, I want a gain of around 10, a little bit more, a little bit less. All right, I want to be able to tweak the gain. So I want my gain to go from like 9, 9 and a quarter, 9 and a half, 9 and 3/4, 10, 10 and a quarter, and so on, like up to 10.75, right? Up to 10 and 3/4 if you were using that same number of bits, all right? Maybe you could have higher resolution. Maybe you don't need that much resolution. But those are the 2 basic ways, and we're going to look at how to do both of those things. Now, the control element is really important in here. You're going to need a control element for every single bit that you're switching. So if you want a 4-bit system, you're going to need 4 control elements. Now, you can use FETs. That's sort of an obvious thing. Or you can use an analog switch. What's the difference? Well, if you're going to use a FET, and what I'm going to do here is I'm going to use P-channel JFETs, primarily because they're readily available. It's a simple sort of circuit setup. It's easy to set up in lab. Why not? Okay. It does have some disadvantages. And those disadvantages can be mitigated by using an analog switch. Essentially, the analog switch will allow you much greater accuracy. And it will allow you to use lower resistor values in your amplifier. And by doing that, you can reduce the noise in the amplifier. You can also reduce its DC offset and its drift. Right? So those are all nice things. You can have a higher performance amplifier. All right? So I'll show you exactly where the insertions, the changes would be in the upcoming circuits. All right? Now, word of caution. What we're looking at here is kind of an introductory thing. This is a very simple sort of circuit. I would not recommend using this circuit for a high precision application, right? Or an application that requires really high resolution. In other words, I wouldn't consider using this for, let's say, a 10-bit system, right? So, 10-bit would be 1024. So you get like 1,000 gain steps. I wouldn't use this. You would probably be better off implementing some kind of digital potentiometer, right? You can get digital potentiometer ICs. The downside of doing that is the interface is usually a little bit more complicated. Typically, you would need maybe a serial peripheral interface kind of thing. Whereas what we're looking at, like I said, you can just hang this off of a port on your little microcontroller. Just parallel interface, wire it up, and you're good to go for the most part. All right? Okay, so let's take a look at what's going on here. First circuit. What I have is an inverting amplifier. And the way I want you to think about this is, think of it in terms of an inverting summing amplifier. So for a moment, forget about all these FETs and these little power supplies. And also, for a moment, forget that all of these things are connected. All of these inputs are connected to the same input signal. So it's like having an inverting summing amplifier, but you're going to use the same signal on each of the inputs, which sounds a little weird, but it's going to make sense in just a sec. So here's the way it works, right? If you just had a simple inverting summing amplifier, you would find the gains for each individual channel by looking at RF over the associated channel input resistors. So for this channel here, it would be 80K over 10K. So you got a gain of 8, right? Inverting gain of 8. And then if you looked at the next one down, right, what I'm calling channel 2 over here, it'd be 80K over 20K, so that's a gain of 4. And then 80 over 40K, that's a gain of 2. And then 80 over 80K, gain of 1. So the actual net gain would be the combinations of these. In other words, the maximum gain you could get would be this gain of 8, this gain of 4, this gain of 2, and this gain of 1, which would be a gain of 15. That's if all of these are active. Another way you can compute this is by just taking the 4 resistors and putting them in parallel, right? Coming up with an RI value that way, kind of figuring out the end result, using that kind of approach. I think it's easier, however, just to look at these as individual input channels, and you'll see why once we start monkeying with this, instead of sitting there with your calculator and trying to figure out precise values for, input resistors. In any case, the switching element over here is a P-channel JFET. And what I've done is to simulate the output from a microcontroller or some other kind of digital circuit, I just have little power supplies here, little DC power supplies. And I've set this up to use plus and minus 5 volts. And that's partly what goes into choosing the JFET that you want. So this one is set up so that a 0 to 5 volt will do the appropriate switching that I want. So if I have 5 volts out of here, this FET will be in the off state. So it's basically an open switch. Okay? End result, this is not being affected. The signal is, it's not creating the appropriate input current and then going through the summing node. On the other hand, if we have 0 volts over here, the FET is fully conducting and we'll get the appropriate current flow into the summing node, right? And we have that for each one of these input channels. Now, ideally, what you want here is 0 ohms conducting and fully open, in other words, infinity, when it's not. One of the tricks with using a simple JFET over here is you really want to find a good switching JFET, something that has a low RDS on value. The higher it is, the more, well, let's say the less ideal, right? The more problems you're going to have, the less ideal the circuit is. The more resistance you have in here, the more it unbalances what the gain is going to be. That's going to create gain error in each one of these input channels, all right? It's also going to exacerbate some other issues, but ideally having a switch, and the closest thing you're going to get to that is an analog switch IC. You can get analog switches that, the on resistance is only just a few ohms, all right? So that's going to work much better. And because, like I said, this internal resistance, this on resistance for your general purpose FET might be, 100 ohms, you realize that to get any kind of accuracy, you're going to need associated input resistors that are, a couple of orders of magnitude larger than that, which is why I've got a 10K over here, okay? So, yeah, that would be a little bit nicer. But like I said, this is just sort of an introductory thing. You can breadboard this and just see exactly how it works, all right? So the same thing happens in these other channels. They're all identical. And right now, I've got 0 volts on each one of them. So each one of these is going to be active, meaning all 4 channels, those gains are going to sum up, and we should get a gain of 15 out of this. Okay? Now, you could use different switching FETs. You could use an N-channel FET. The problem with using an N-channel FET is you would now need a negative voltage for your logic. Right? So it would be going 0 would be on, but you'd need like a negative 5 volts or something like that to turn it off. The other option would be to get an N-channel enhancement mode MOSFET, in which case 0 would be the off state and the plus voltage would be the on state. Okay? So that would be maybe a little bit more typical in terms of the way we think of activating a switch. Okay? Could you use bipolar transistors? Well, yes, but if you try it, you'll find out that you're going to have some issues with DC offset. That's going to be exacerbated. So, this is, like I said, a sort of a good starting point. All right. So anyway, let's just do a little transient analysis. Like I said, this thing should have a gain of 15. 100 millivolt input signal, we should be looking at about 1.5 volts peak coming out of this thing. Okay. So we'll do a little transient analysis. And where is our, here it is. Okay, so VN is the little green thing. We have the inversion as we would expect because it's an inverting summing amplifier. And we can see that we're getting a nice big signal over here. So let's just go measure this. I'll move this guy over just a little bit. And so we're getting just a little bit over 1.5. But there is a little bit of a DC offset in here, I can see. If we come down to here, yeah, see, we're getting like 1.4 something negative. So there is a little bit of DC offset, but we are getting the gain approximately that we would expect. Okay? So that's good. I'm pretty happy about that. Now, just to kind of prove the point, come in here and change one of these, right? So let's turn this one to 5 volts. So that's going to turn off this channel, right? This 5 volts is going to be essentially an off voltage for this P channel FET. So this is off. We're only going to get gain through these 3. So that's a gain of 1, 2, 4, or 7, right? This is the gain of 8 for this one up here. This is going to be the extra gain of 7. So now we should only have about 700 millivolts coming out. And voila. Okay, so I can see there's 700 right there. 700. I think it's pretty much the same kind of offset issue we had last time. Yeah, so we're a little over 700 millivolts, and we're a little bit negative of 700, so yeah, that works great, okay? If DC offset is a problem, you could just put a coupling cap out here, right? All right, so you could use a quad analog switch, an SPST analog switch. And depending on the quality and the type and the logic level, you might be able to get that for cheap, like under $1, under $1. So that might be something you'd be interested in experimenting with. And if you did that, if it was a decent one, like I said, that had, just a few ohms for the on resistance, well, hey, you could easily knock down all these resistors by, a factor of 10, right? Make that a K, 2K, and so on and so forth. Make this 8K. If your input source is particularly sensitive to that, you could always put a buffer out here to give you a higher input impedance. All right. But having those lower resistors would reduce that issue that we just saw with the DC offset, right? Because that's largely driven by, external resistor sizes and things of this nature, right? Certainly that's going to be the case with an op amp. Now, the TL071 is a FET input op amp, so the currents aren't so bad, but the VOS, the DC offset there on the input end, VIO, kind of high, maybe 3 millivolts, something like that. If you had a newer FET like an LF411, FET front end op amp, the newer generation, that would be down by, an order of magnitude or more. So what we just saw for the offsets would not be as bad. All right. Okay. So this is all well and good. I'm going to kind of do this programmatically instead of just sitting here and changing these things one after another, because that can get kind of tedious. I set up something a little bit different, basically the same circuit, but what I do is I have square waves driving each of these inputs. Okay, so if we look at this one, this is the least significant bit. So I want to change this one really fast because I want to count 0, 1, 2, 3, 4, 5, 6 automatically. So I'm putting in a square wave, right? It's sitting on a DC offset of 2.5 volts, and it's a 2.5 volt peak. So it's going to go from 0 to 5 volts, right? And this is sitting at 500 hertz. Why 500 hertz? Because this part, right, half a cycle is going to be a millisecond long, and I'm using 1 kilohertz over here. So 1 full cycle of this is the millisecond. So what's going to happen is I'm going to get a cycle at a gain of 0, a cycle at a gain of 1, a cycle at a gain of 2, a cycle at a gain of 3, and so on and so forth up to 15. And then this is going to reset itself, right? Because if I look at this one, some of you who've done a lot of digital work are probably already ahead of me on this. But if you're not, just bear with me. So this one's coming in at half the frequency at 250. This one is coming in at half that frequency, right, at 125. And you can guess that the last one is coming in at half that frequency, all right, at 62.5. So that's what's going to happen. We're going to get these bit patterns that are essentially going to count up, right? You've probably made like little truth tables and things like that. So you count up, all zeros, 1, right? Then 0010, 0011, 0100, 0101, and so on and so forth. So that's what these sources are going to do. They're going to generate that sort of pattern. But like I said, ultimately, these 4 things, these would be the pins coming out of your digital logic circuit or your microcontroller. If it's your microcontroller, you can write code to just write, a 4-bit set of values to that output port. You hook it up and off you go. Just make sure that the output levels are compatible, right? So in any case, something interesting is going to happen here that you might not have expected. Let's see. Bonk. Okay, so there's a lot of stuff here. I mean, there's these 4 things, this input plus the output, and you can see that there is a sine wave here, right? And it turns out that sine wave is the output sine wave. There's a little tiny sort of a blue-green sine wave in here, and that is the input signal. So you can see how this is growing the way it should. I'm going to separate these out. Well, of course, we have all this other stuff, which is the logic going up. But there is another little thing here. Okay, I want to look at the logic stuff first, right? So here's the bit number 4 over here, right? So you can see this is high, low, high, low, high, low. And then this goes up half that, and then finally half that. So remembering that this is engaged on a low, right? So this is like 0, 0, 0, 0. So this should give us no gain. And then this is 1, 0, 0, 0. We get a little bit of gain. And then this is 0, 1, 0, 0, right? 0, 1, 0, 0. And we keep on going, right? 1, 1, and so on and so forth, right? So this just keeps building. But you notice we've got some spikes in here. All right, now to make this a little bit easier to see, I'm going to get rid of some of the curves. I'm going to get rid of some of these sort of timing curves. So we just have the input and the output. All right, so here's our nice input, 100 millivolts. Here's our load. Notice this is on a 10-volt scale because there are some switching spikes. Geez Louise, switching spikes. I don't want to see switching spikes. Let's zoom in on this a little bit so we can see this a little better. All right, so you can see that there's this nice sine wave. It's going from this 0. There's the gain of 1, the gain of 2, and it works its way up to the gain of 15. Right? So if you just count up, that's what you're going to get for a gain. Right? Beauty. Well, I'm not really excited, enthused about all these switching spikes. What can we do about that? Well, in some applications, it's not really going to make much difference. If you're going to cycle through things very quickly, and if this was like an audio kind of thing, you're going to hear these ticks and pops going through. That's not too cool. You basically have a couple of ways of doing it. You can slow down the edges on these sources through a little RC network. You make a little lag network, all right? So, like maybe a couple K ohms here, and then you got like 10 nanofarads or something like that. All depends on how fast you really need to switch, but that is what would feed the gate of the FET. So you would run the port bit, right? So imagine that's coming in over here. So you'd have resistor in, cap going down the ground. So that slows up the edges, and that's going to clean up things. The other thing you can do is insert a little lag network at the output. You just have to make sure that critical frequency is at least as high as the highest input frequency you expect to use. Otherwise, it's going to start filtering your input frequency. All right, so this is only 1 kilohertz. So what I'm going to do is I'm going to go to the next level and show you this, and I'm going to include that. But the big thing on the next level is I want to show you how to do the narrow range control. All right, so those things we just looked at were basically 0 up to some maximum. So this version is, here's the set gain. I want to go from gain A to gain B. I want to go from 8 to 6. Excuse me, I want to go from like 8 to 10 or 15 to 20 or something like that, okay? So what I've set up here is something that goes from basically 9 to 11. Not quite, but about that. What you do first, notice the first channel here doesn't have the switch. So this is your base gain. You put in the RF and the what I'm calling our 0 over here. Right? This one never gets switched out. So 100K over 11.11K is going to get you a gain of 9. All right. Then you look at the little pieces that go along with it. So 100K over 100K, that's 1. 100K over 200K, that's a gain of a half. And then 100 over the 400K gives me a gain of a quarter, right? So you can have as little as this, which is a gain of 9, or this plus each of these, and this will establish your resolution. So this is going to go up by quarter steps, okay? So this is going to take you up to just 1/4 shy of that upper gain of 11. Now, on the output end, I've put a little lag network here to reduce the spikes. Right, this is one thing you can do. Unfortunately, you're going to lose a little bit of signal. I got a 10K load, and the lag resistor here associating with C lag is 1K, so we're going to lose about 10% of our desired signal. Like I said, it's a simple way of doing it. There's other ways of doing it. You can do a little filtering right across RF. You can put a little cap across RF, which will do a similar sort of thing. But I wanted to put this out here in an obvious sort of way so that you could see it, because I want to show you how effective it can be. Here's the signal right before the lag network. In other words, this is the raw op-amp output, and then here's the filtered. That's our V-load. All right, so this is set up the same way, except I'm just using 3 bits over here, but this thing is going to count through kind of like the other one did. So let's do a little transient analysis. Okay, so on this one, I'm only looking at the 2 major signals of interest, which was V-load and V-out op-amp. So the maroon one is V-out op-amp, and you can see there are these big spikes in it. And then the green one is V-load. That's the filtered one. All right, you can see a little phase shift caused by the lag network. But let's separate out those curves, okay? Get him out of here. All right, so there's still a little bit of the glitching here, right, where you got the really big spikes. You can still see there's a little bit of glitching, but it's nicely cleaned up. And in this version, you can also see the way the gain is increasing, right? It's going from a fairly modest gain over here. This is, like I said, like our gain of about 9. And then up here, we're getting a gain of about 11. But as I said, we're losing a little because of the lag network, so it never gets quite up to 11. We're only getting up to about 10. And then it recycles and starts at the low gain and works its way back up again. Okay, so that's kind of cool because it shows you, how you can sort of have this thing be in a sort of like a sub-range. You don't have to go from 0 to a max. You can go from one level to another level. All right. Okay. So, a fun circuit to kind of monkey with. You have little projects, like with an Arduino board or something like that. This can be pretty useful, right? Like I said, for super high accuracy, I wouldn't go this route. Certainly high resolution, because high resolution is going to require a lot of inputs, right? A lot of these channels. And what ends up happening is these resistors wind up getting really huge, right? I mean, these keep doubling basically if you want to do it this way. So pretty soon you're going to have a value that's way bigger than this. And you don't want megohms. The offsets and so forth and noise are going to be pretty ridiculous. If you're familiar with this, you might be saying, well, could I configure an R2R ladder network? The answer is yes, you could. You could do that, in which case I wouldn't go with FETs. You'd actually need 2 FETs, one to engage and one to switch over to true ground rather than the virtual ground of the summing node. You're probably better off getting an analog switch that's single pole double throw right, an SPDT, so that the switch would be throwing either to the node or to ground, right, to true system ground, or to the virtual ground of the summing node, instead of just interrupting this, right? That would be required for the R2R. So in other words, your inputs over here, you'd have R, and then these would be like 2R. You'd have an R here, 2R, R, 2R, and so forth, right? In other words, you're using the R2R network in current mode rather than in voltage mode, right? All right, so you could do that. But like I said, ultimately, you need really high resolution and high accuracy. You're probably better off going towards a digital potentiometer. But again, the interface for that's going to be a little bit more involved. All right. So a fun thing to play with. Give it a shot. Tell us what you think. Until next time, this is Professor Fiore saying, have a good one.